Hello. So now we're going to finish, this is our second lesson in our second set of videos for energy, and we're going to finish up the notes that I gave you for the first day before our test. So I'm on page 6 of the notes, and I'm going to talk about state functions. Okay, now we're going to talk about something called state functions and path functions. These are weird vocabulary words, but don't worry about it. We'll figure them out. So a state function just means something you can measure that does not depend on the path you take. A path function is something you can measure that does depend on the path you take. So we're going to use a mountain as our first example. I'll make my mountain a little bigger if I can. Now, a state function would be, for a mountain, would be the height of the mountain, because, let's move this out of the way, no matter how you get from the bottom to the top, the height of the mountain is the same. Whether you walk around the mountain and around the mountain, here you are walking with your backpack, and you get to the top, the height that you have gone up is the same, whether you did it that way or if you took a helicopter. That's my helicopter, and you flew up and you landed over here. Either way, you've gone the same height. However, the distance you traveled, we'll write D for distance over here, and I should take a step backwards before we go to D, cross out D. State functions, where they don't depend on the path, we write them in capital letters. So I'm going to write my H for height here in a capital letter. Over here, I'm going to put my D in a little letter, because D is going to turn out to be a path function. The distance I travel very much depends on my path. If I take this long way and I just walk around and around and around and around, the distance will be much longer than if I were to just take my helicopter and fly like that, or if somehow I were magically able to walk just straight up the side. The distance is going to be different, so distance depends on path. And that's the difference between a path function and a state function. Go back to our words. A state function does not depend on the path you take. So for a mountain, we could say that was the height. A path function depends on the path you take. For a mountain, that could be the distance. Let's look at an example for chemistry, not mountains. So we'll take this out of the way, and we'll make this picture bigger. Internal energy is a state function. We're going to write it as a big E. When we talk about the change in internal energy, we're going to use our triangle for change, our delta change, and big E. Because the internal energy of a system does not depend on what you do to get there. If you have water at 25 degrees Celsius, and you have 50 grams of water, that water has a certain amount of energy. Whether you heated it up really slowly, whether you heat it up really fast. If you took water that was, I'm going the wrong way here, if you took freezing water and you heated it all the way up to 100 degrees Celsius and then cooled it down, it doesn't matter what path you take, at 25 degrees Celsius, this mass of water will have a certain amount of internal energy no matter the path, because the internal energy is based. The internal energy depends on the molecules moving around in there, and they have a certain amount of energy at a certain temperature. However, the heat that you use to get to this temperature, we represent heat with a little q, heat is a path function because it's a method of transfer. And so the amount of heat that you put in to go, let's say if you go from 0 degrees to 25, that's going to be a certain amount of heat. But if you went from 0 to 100 and then cooled it down, well, you'd put in more to get from 0 to 100, and then you take some away. So heat depends on the path. Energy does not. And when you see letters that are big, they're going to be things that don't depend on the way you get there. Little letters do depend on the way, and that will have some more meaning going forward. Okay, now we're going to define something called enthalpy. So, because in our world, many processes, like photosynthesis, where the leaves are turning the sun's energy into food, or water evaporating from a lake, or even when we're in this laboratory and we're doing reactions in our beaker, all these types of things can be accompanied by heat. Heat either being lost or heat being gained, or who knows what's happening over here. They can be accompanied by heat being released or absorbed, and also they can be accompanied by work that's being done on the system. For example, when this water vapor goes up into the atmosphere, it's going to create clouds that will create wind, which is doing work. Here we could create a gas that would do work on a piston. So it would be nice to have a state function that would relate the amount of heat that's being transferred to the amount of energy. So I was saying it would be nice to have a state function that could relate heat to energy, because state functions are the same no matter how you get there. Turns out we do have one. We're going to define something called enthalpy. Let me make my pictures smaller. We're going to define enthalpy, and we're going to call it our enthalpy. We're going to use the symbol H for enthalpy, and we're going to define it as the amount of internal energy of a system plus the pressure volume work that is done by the system. And I'll talk about work right now, actually. But because in our world we're pretty much at constant pressure, this will work because we're under atmospheric pressure. So enthalpy is equal to internal energy for E plus pressure times volume. And that is, this pressure times volume is going to end up being work. So what should I talk about first? And because internal energy is a state function, pressure is a state function, volume is a state function, therefore enthalpy is going to be a state function. So now we're going to talk about why P times V is work. So previously in this set of notes we talked about how work equals force applied over a distance, or force times distance. And we had this picture, I believe, where we had a gas in a container and it expanded. There was a reaction that took place. Well, actually, let's pretend there's a reaction that takes place. And I want to use an opposite example. So we talked about how work could be done if the gas expanded, or if the piston went down. That was a force being applied, and the distance would be, the distance changing here. I'm going to use a different example right now. Here I have zinc being put into this vessel, and there's hydrochloric acid in here, and they're going to react. This is a single replacement reaction, folks. You just were tested on this. This would be the full reaction, zinc solid plus 2HCl going to zinc chloride plus H2 gas. And when the gas is created, it has more volume, gas expands, and so it will go up here and push this piston up. So we're going to look up at this little measuring system. An increase in volume means the system, whatever's inside here, is doing some work. It's pushing this piston up. So you can assume that the whole thing is under atmospheric pressure, because we have atmospheric pressure that's pressing down. Air outside is pressing down on this piston. But there is a change in volume. That's our distance. Our force is our pressure, but our distance is going to be the change in is going to end up being the change in volume, because the area stays the same. So the piston goes from here up to here. So we have a change in volume. So we can describe this force times distance. The force is the pressure, and the distance ends up being the change in volume, because volume is equal to area times distance, and it's our height, or our distance, that's changing. So we can rewrite work as being equal to pressure times a change in volume, because our volume changed when work was done, when the gas was created. Now, so we're going to say work is equal to pressure times change in volume, because we're saying this is equivalent to force times distance. because the P is our force and volume is area times, I'm going to call it distance instead of height, and what really changed here is our distance. Our area stayed the same. So let's look and see what the sign will be of our work, if it's going to be positive or negative. So in this case, our change in volume is going to be our final volume minus our initial volume. And here our final volume is greater. So our gas was created, and our change in volume when our gas is created is going to be positive. I'm going to write a plus because our final volume is bigger than our initial volume. And in this case, the system did work because the gas was created and it pushed up. So when work is done by the system, work is going to be positive. And I believe you have that on your little chart at the top of page 6. You'll see 4W at the top of it, and it says a plus sign oh, wait a minute, what am I telling you? Okay, I forgot something over here, don't kill me. And this gets into sign conventions, whether we say things are positive or negative, and I think this is slightly different in physics. So if you're taking physics, you'll see it opposite. In chemistry, we say that work is equal to minus pressure times the change in volume. So go back to wherever you wrote this down. Say work is equal to the opposite of pressure times the change in volume. Now, back to where we were. Our final volume is bigger than our initial volume. Go back. And so our change in volume here is positive. So our change in volume is positive, our pressure, our atmospheric pressure is positive, our sign on our work will be negative, and you'll see that at the top of the page on page 6. It says minus means work's being done by the system, and that's what happened here. We made a gas, the gas did work, so the system did work, it pushed the piston up, and the way that'll play out is that the sign on our work will end up being negative, because work is the negative of pressure times delta volume. And if the opposite were true, if our final volume, we'll do it in a different color, if we were not working with this picture, if we had a completely different picture, and our final volume was less than our initial volume, that would mean that the atmosphere had pushed our piston down. So that would mean that the atmosphere did work on our system, or work was done on our system. In that case, delta V would be negative. It would get substituted in here. It would be a negative number, and a negative of a negative would be positive. So if work is done on the system, the sign should be positive. And you'll see that at the top of page 6, and if that seems a little confusing, I understand. But you'll just have to get used to working with it. Let's go back to enthalpy. Enthalpy was H, and we said enthalpy was equal to internal energy plus pressure volume. So if we say that, we can say our change in H, our change in enthalpy, is equal to our change in internal energy plus our pressure times our change in volume, which is our work. Now, why is this equation going to end up being handy at constant pressure? Why do we say, well, at constant pressure, this is a helpful state equation to have? Here's why. Early in our notes, we said that this delta E, let's do it in purple. We said delta E was equal to heat plus work, right? And so let's just keep this over to the side. We were just talking about pressure and volume, and we said that that work on the previous slide was equal to the opposite of pressure times the change in volume. So let's substitute in this. If this is true up here, then that means that the opposite of work is equal to pressure times change in volume. So we're going to substitute in minus W for PWV here. So then this becomes change in enthalpy equals the change in internal energy minus work. Now we're going to substitute in this for delta E. So I'm going to say my delta H is equal to heat, small q, so that's heat, that's a path function, but it's heat being transferred, plus work, also a small letter, path function. That I'm substituting in for this change in energy. Then I have to minus work. So what do we have left? We have left that at constant pressure, our enthalpy is going to be equal to just Q because these cancel. So this is at constant pressure. I'll make another box because we defined that at the beginning. At constant P, our change in enthalpy will be equal to heat transferred. And that's going to come in very handy when we look at heat being released or absorbed in equations. We'll be able to figure out the enthalpy of those equations. So I'm going to stop here. I'll finish up the last pages 7 and 8 of these notes when I start the 3.2 notes in the next video.